There is something lurking at the center of nearly every galaxy in the universe. Something that devours stars, bends the very fabric of reality, and creates regions where time itself grinds to a halt. And the most unsettling part? It is not actually an object. We call them black holes, but that name is deeply misleading. A black hole is not a thing floating in space the way a planet or a star is a thing. It is a wound in the geometry of the universe, a place where the normal rules of space and time have collapsed so completely that our physics breaks down entirely. Everything we think we know about cause and effect, about up and down, about past and future, stops working at the edge of a black hole. And that is exactly why they matter. Because by studying the places where the rules break down, we learn something profound about the rules themselves. In this video, we are going to take a journey through the life and death of a black hole, from the violent stellar explosions that create them, to the bizarre quantum tricks that ultimately destroy them. We will explore a phenomenon called Hawking radiation, a process so strange it forces us to ask whether the matter inside a black hole is even real in a meaningful sense. We will look at how spinning black holes tear spacetime into a whirlpool, and how we might one day extract enormous amounts of energy from that whirlpool. And at the end, we will look at the mathematical mirror image of a black hole, an object that spits matter out instead of swallowing it, and ask the most mind-bending question of all: could our entire universe be one of those objects? Let's start at the beginning. Let's start with a star. Every star in the sky is a war. On one side, gravity, the crushing, relentless pull of the star's own mass, trying to collapse it into a single point. On the other side, nuclear fusion. Deep in the star's core, hydrogen atoms are being slammed together with such force that they fuse into helium, and that process releases an enormous amount of energy that pushes back outward against gravity. This balance is called hydrostatic equilibrium. As long as the star has hydrogen to burn, the two forces stay roughly equal, and the star remains stable. But hydrogen is not infinite. Eventually, it starts to run low. For smaller stars like our Sun, this is where the story ends. The star swells into a red giant, sheds its outer layers, and the core becomes a dense, slowly cooling remnant called a white dwarf. Dramatic, but relatively quiet. For massive stars, the giants 8 or more times the mass of the Sun, the story is far more violent. When hydrogen starts to run out, the core contracts and heats up until it can fuse helium into carbon. Then carbon into neon. Neon into oxygen. Oxygen into silicon. Each fusion stage burns faster than the last, and each one produces a new element. The star is building up layers, like an onion, with heavier elements at the center. And then it reaches iron. Iron is where the fusion chain terminates. The reason is thermodynamic. Every previous fusion reaction released energy because the resulting nucleus had less internal energy than the components going into it. That leftover energy is what powers the outward push. But iron is different. Iron is at the very bottom of the nuclear binding energy curve. Fusing it doesn't release energy, it consumes it. Iron just sits in the core, piling up, contributing nothing to the fight against gravity. And then, in a fraction of a second, the scales tip. The iron core collapses. What happens next is one of the most violent events in the observable universe. The core rebounds off itself in a shockwave that blasts through the entire star, ejecting its outer layers at a significant fraction of the speed of light. We call this a supernova. For a brief period, the explosion can outshine an entire galaxy of hundreds of billions of stars. But the shockwave leaves something behind. If the original star was massive enough, the core that remains is not a neutron star, a dense ball of neutrons roughly 25 kilometers across. Instead, the core keeps collapsing, and collapsing, and collapsing. There is nothing left to stop it. Our physics reaches a point it cannot describe, and what remains is a singularity, a point of theoretically infinite density, wrapped in a sphere of no return. We call that sphere the event horizon. And that is where things get truly strange. When you look at a photograph of a black hole, the kind that made headlines in 2019 when the Event Horizon Telescope first imaged one, you are not seeing the black hole itself. You are seeing its shadow. The dark circle at the center of that glowing ring of superheated matter is the event horizon, the boundary beyond which nothing, not particles, not information, not even light, can ever return. It is not a physical surface. There is no wall there, no membrane you can touch. It is a geometric property of spacetime, a threshold defined entirely by the fact that gravity, past this point, has become so overwhelming that the escape velocity exceeds the speed of light. Think about what escape velocity means. When a rocket launches from Earth, it needs to reach about 11 kilometers per second to break free from our planet's gravity. If you were standing on a neutron star, you'd need to move at roughly half the speed of light to escape. At the event horizon of a black hole, you would need to exceed the speed of light itself, and nothing in the universe can do that. So anything that crosses the event horizon is gone. From the perspective of the universe outside, it has ceased to exist in any practical sense. But here is where things get philosophically disturbing. Time itself behaves differently near the event horizon. Einstein showed us that gravity and time are inseparable. Mass warps spacetime, and that warping affects the rate at which time passes. The stronger the gravitational field, the slower time runs. This is not science fiction, it is measurable. GPS satellites have to account for it because they experience weaker gravity than we do on Earth's surface, so their clocks run slightly fast. We adjust for this every single day. Near a black hole, this effect becomes extreme. If you watched an astronaut falling toward the event horizon, you would see them slow down. As they approach the boundary, their movements would become more and more sluggish. Their signal would redshift into radio waves, then into silence. From your perspective, they would never actually cross the horizon. They would appear to freeze there, dimming into invisibility. Time, for them, would appear to stop. From the astronaut's perspective, though, they would cross the event horizon without necessarily noticing anything unusual in their immediate surroundings. The passage would feel normal. What they would eventually notice, if they survive long enough, is that the entire future of the external universe would appear to play out in an instant above them. The time dilation is so severe that from inside the event horizon, the outside universe ages faster, in a sense. And beyond the horizon lies the singularity, a point where our equations spit out infinities and stop making sense. We do not have a theory that can describe what happens there. It is one of the great unsolved problems of modern physics. But something remarkable happens before you even reach the singularity. Something that changes everything we thought we knew about what black holes can and cannot do. For most of the 20th century, it was assumed that black holes were permanent. Once formed, they would exist until the end of time, growing larger as they consumed matter, but never shrinking, never dying. The event horizon was a one-way door, and everything that fell through was lost forever. In 1974, Stephen Hawking turned that assumption on its head. His paper, titled Black Hole Explosions, proposed something radical. Black holes slowly evaporate. They lose mass over time by emitting radiation, now called Hawking radiation, and eventually, over timescales vastly larger than the current age of the universe, they vanish entirely. This seems impossible. If nothing can escape a black hole, how can it radiate energy? The answer requires us to understand something deeply strange about the nature of empty space. What is nothing? Take a volume of space, a cubic meter of absolute vacuum.
No atoms, no dust,
no light passing through. Is that nothing? The answer, according to quantum field theory, is no. Completely empty space is not nothing. It is a seething, churning field of quantum activity that only looks calm at the macroscopic scale. To understand why, we need to introduce the concept of quantum fields. In the modern picture of physics, every particle is not really a particle in the traditional sense. It is a localized vibration, an excitation, of an underlying field that permeates all of space and time. There is an electron field, and electrons are ripples in that field. There is a photon field, and photons are ripples in that field. Every type of particle corresponds to a field, and these fields fill the entire universe. Now here is the key insight. These fields are not completely still, even in regions we call vacuum. Because of a fundamental principle of quantum mechanics, Heisenberg's uncertainty principle, the value of any quantum field at any given point can never be perfectly nailed down to zero. There is always some residual quantum uncertainty. And the consequence of this is that quantum fields constantly fluctuate, even in empty space. This fluctuation does something extraordinary. It causes particle-antiparticle pairs to momentarily pop into existence, a particle and its antimatter counterpart, created from nothing, existing for an immeasurably short time before annihilating each other and vanishing back into nothing. These are called virtual particles. They are not metaphors or theoretical constructs. There is direct experimental evidence for their existence. This evidence is called the Casimir effect. In the 1940s, physicist Hendrik Casimir predicted that if you placed two uncharged metal plates very close together in a vacuum, they would experience a tiny attractive force pushing them together. Why? Because the space between the plates restricts which virtual particle pairs can form, only pairs whose wavelength fits between the plates can appear in that region. Outside the plates, all wavelengths can form. The result is a slightly higher virtual particle density outside the plates than inside, creating a pressure difference. The plates are pushed together by nothing, by the quantum noise of empty space. The experiment has been done many times. It works. Virtual particles are real. Now, what does any of this have to do with black holes? Hawking realized something profound about what the event horizon does to this quantum vacuum. Normally, virtual particle pairs form and annihilate almost instantaneously. They are borrowing energy from the uncertainty principle, and the universe demands it back quickly. But at the boundary of a black hole, something different can happen. If a virtual pair forms just outside the event horizon, there is a chance, a quantum mechanical probability, that one member of the pair falls inside the horizon before the pair can annihilate. The other member, finding its partner gone, can no longer recombine. It becomes a real particle, carrying real energy away from the black hole. But energy must be conserved. If a real particle with real energy is escaping the black hole, something must pay that energy bill. And the something that pays is the black hole itself. The mass of the black hole decreases slightly with each Hawking radiation event. Over vast timescales, this process drains the black hole entirely. There is a further implication that is even more disturbing. The temperature of Hawking radiation is inversely proportional to the mass of the black hole. A stellar mass black hole emits radiation at a temperature so cold, billionths of a degree above absolute zero, that it is completely undetectable against the cosmic microwave background. But as the black hole shrinks, its temperature rises. As it approaches its final moments, the process accelerates dramatically, culminating in a burst of energy release. A black hole does not just evaporate, it explodes. Now, this has not been directly observed for real black holes. They are all far too large and the radiation far too cold to detect. But in 2016, researchers at the Technion Institute in Israel built an analog of a black hole using a quantum fluid, a configuration where phonons, sound quanta, cannot escape past a certain boundary, mimicking the way photons cannot escape past an event horizon. They ran the experiment 97,000 times over 124 days and detected radiation matching Hawking's predictions with remarkable precision. The math works. And if the math works for sound, it almost certainly works for light as well. The existence of Hawking radiation is strange enough on its own, but it carries an implication that is perhaps the most philosophically unsettling idea in modern physics, an idea that calls into question the nature of physical reality itself. Here is the issue. Hawking radiation does not come from inside the black hole. It does not come from the singularity or even from the event horizon itself. It is generated in a region of space outside the black hole, a region potentially billions of kilometers away from the horizon, purely as a consequence of the way the black hole curves spacetime. The radiation is not escaping from inside. It is being created outside. This means something strange about the relationship between the black hole and its radiation. Normally, we think of causes as producing effects. A fire produces heat. A moving object produces a wake. The black hole, with all its mass, all its gravitational power, produces a curvature of spacetime around it, and that curvature produces Hawking radiation. The mass causes the curvature, causes the radiation. That is the order we intuitively expect. But Einstein's equations for general relativity do not specify that this ordering is mandatory. The equations relate mass and spacetime curvature, but they do not say which one is the cause and which one is the effect. The relationship is proportional, not directional. You can run the equations forward or backward. This is where Hawking radiation becomes philosophically explosive. If the curvature of spacetime radiates energy, and if that radiation reduces the curvature, and if the reduction in curvature reduces the mass, then the sequence of causality is inverted. The curvature is not the shadow cast by the mass. The mass is the shadow cast by the curvature. Let that sit for a moment. What we experience as solid matter, as mass, as substance, might not be fundamental. It might be a projection, a consequence of the geometry of spacetime. In this view, space is the primary reality, and matter is what happens when space is severely bent. Think of it this way. Hold your hand up and project a light at it. The shadow on the wall is real in the sense that you can observe it and describe it. But it is not fundamental. It is a consequence of your hand's geometry interacting with the light. If you move your hand, the shadow changes. The shadow is downstream from the hand. The projection hypothesis about matter is saying, what if we are the shadow? What if the curvature of spacetime is the hand, and what we experience as mass and substance is merely the observable consequence of that curvature? What if matter, like the shadow, is real in a derived sense, but not fundamental? This is, to be clear, not an established fact. It is an implication of the mathematics, a possibility that the equations permit but do not definitively prove. But it is a genuine scientific hypothesis, not merely philosophical speculation. And here is what makes it genuinely disturbing. You cannot tell the difference from the inside. If you were a shadow and you did not know it, how would you know? From inside your reference frame, you would have experiences, thoughts, a sense of continuity. Reality would feel solid and real. You would have no way of distinguishing between being a primary entity and being a projection of one. Black holes, by breaking the normal rules of spacetime, offer us a lens through which we can ask questions about those rules that we could not otherwise formulate. And some of the answers that come back are uncomfortable. Not all black holes are the same. The simplest black holes, what physicists call Schwarzschild black holes, are those that neither spin nor carry electric charge. They are perfectly spherical, utterly static, and described by a single number, their mass. But in the real universe, virtually every black hole spins. When a massive star collapses, it conserves angular momentum, the same principle that makes ice skaters spin faster when they pull in their arms. As the star's core contracts from thousands of kilometers across to a few kilometers, any initial spin at it gets amplified enormously. Real black holes rotate at close to the maximum rate physically possible, and that rotation does something remarkable to the spacetime around them. Einstein showed us that mass warps spacetime. What he also showed, though it took longer for the implications to be appreciated, is that a rotating mass does something more. It drags spacetime along with it as it rotates. Imagine spinning a bowling ball in a pool of honey. The honey near the ball would begin to rotate too, not because it was pushed, but because the rotation of the ball drags the fluid around it. This is called frame dragging. For ordinary objects like the Earth, frame dragging is real but incredibly subtle. We can only detect it with the most sensitive instruments in existence, like the gravity probe B satellite. But around a rapidly spinning black hole, frame dragging is not subtle. It is violent. Around a spinning black hole, there exists a region outside the event horizon called the ergosphere. It gets its name from the Greek word for work, ergon, because this is a region where work can, in principle, be extracted from the black hole. Within the ergosphere, the dragging of spacetime is so extreme that it is physically impossible to remain stationary. Even if you were directing all your thrust against the rotation, you would still be dragged around the black hole because the space you are sitting in is itself rotating. You cannot stand still in the ergosphere any more than you can stand still on a moving walkway. What is even more extraordinary is the speed at which this spacetime rotation occurs. Near the event horizon of a rapidly spinning black hole, the ergosphere reaches speeds where spacetime itself is moving faster than the speed of light. But this does not violate Einstein's rules, because those rules only prohibit objects from moving faster than light through spacetime, not spacetime itself from moving. This creates an extraordinary situation. Deep in the ergosphere, matter is being dragged around at an appreciable fraction of the speed of light, purely by the geometry of spacetime. No force is being applied. It is not being pushed. It is simply moving because the stage on which it sits is moving. And if you can extract that motion, you can extract enormous energy. Energy not from matter falling into the black hole, but from the rotational kinetic energy of spacetime itself. This is the Penrose process. The physicist Roger Penrose proposed a mechanism by which an object entering the ergosphere could, under the right conditions, split into two parts. One part falling into the event horizon on a trajectory that reduces the black hole's angular momentum, and the other part being ejected outward carrying more energy than the original object brought in. The excess energy is real, and it comes from the rotational energy of the black hole. Theoretical calculations suggest that up to around 21% of the black hole's total mass energy could be extracted this way, and because of Einstein's E equals mc squared, that represents a staggering amount of energy. A single kilogram of mass energy extracted from a black hole via the Penrose process would release the equivalent of about 15 kilotons of TNT. This is not quite science fiction. It is a real mechanism consistent with general relativity. Whether humanity could ever engineer such an extraction is another question, but the universe does not seem to have prohibited it in principle. Here is a question that sounds like it belongs in a science fiction novel. If black holes are defined by the property that nothing can escape from inside them, do their mathematical opposites exist? Objects from which nothing can fall in. where matter and energy can only flow outward? The answer, at least mathematically, is yes, and they are called white holes. To understand white holes, we need to think about how physicists describe the geometry of spacetime around a black hole. One of the most useful tools for this is something called a Penrose diagram, a way of mapping all of spacetime, including its infinite past and infinite future, onto a finite picture. The rules are elegant. In a Penrose diagram, light always travels at 45-degree angles. Anything that must travel slower than light, which is everything with mass, can only move at angles steeper than 45 degrees. Draw the Penrose diagram for a standard, non-rotating black hole, and you get 4 regions. Region 1 is the normal universe, the observable cosmos, stretching from infinite past to infinite future. Region 2 is the black hole interior, separated from the universe by the event horizon. You can see in the diagram why it is a one-way door. Any path that crosses the horizon, traveling at 45 degrees or steeper, inevitably hits the singularity. There is no path that leads back out. But the mathematics of general relativity are symmetric in a certain deep sense. When you solve Einstein's equations for a black hole, you do not get just regions 1 and 2. The complete mathematical solution contains 4 regions. And region 3, sitting on the other side of the singularity, is a region with a singularity in its past rather than its future. In this region, light can leave but not enter. Matter can escape but not fall in. It is the time reversal of a black hole, a white hole. Now, before you get too excited, no white hole has ever been observed, and there are strong reasons to think that the white holes predicted by the simple mathematical solution may not survive in the messy real universe. Black holes in reality form from collapsing stars, and this formation process breaks the mathematical symmetry that creates the white hole in the theory. So white holes may be mathematical artifacts, features of the idealized equations that do not correspond to anything in the physical universe. But there is a more speculative and intriguing possibility that has gained serious attention in recent years. When Hawking radiation eventually evaporates a black hole down to the Planck mass, around 22 micrograms, our standard equations of quantum mechanics and general relativity stop being reliable. We enter a regime that requires a full theory of quantum gravity, which we do not yet have. One candidate theory, called loop quantum gravity, suggests that something remarkable happens at this scale. Instead of the black hole collapsing into a true singularity, quantum effects prevent the collapse. The black hole bounces, and when it bounces outward, it becomes a white hole, slowly radiating its stored information back into the universe. This is deeply significant because it offers a potential resolution to something called the information paradox. If matter falling into a black hole is truly destroyed, if the information encoded in that matter is permanently lost, then this violates a fundamental principle of quantum mechanics, which says that information can never be truly destroyed, only scrambled. Hawking radiation alone doesn't solve this problem, because standard Hawking radiation is thermal. It carries energy but not information. The loop quantum gravity white hole scenario suggests that all the information that fell into the black hole over its lifetime is eventually, slowly, over timescales almost incomprehensibly vast, radiated back out through the white hole phase. This is speculative, but it is grounded in real mathematics and addresses a real problem. And there is one more implication, the most staggering of all. In general relativity, our universe has a singularity in its past. 14 billion years ago, at the moment of the Big Bang, all the matter and energy in the observable universe was compressed into an infinitely small, infinitely hot point, a singularity, and then expanded outward. In the language of a Penrose diagram, our universe looks, from the outside, like a region with a singularity in its past from which matter is flowing outward. That is exactly the definition of a white hole. Our universe, in the most literal mathematical sense, is consistent with being the interior of a white hole. Not a black hole, we are not being crushed inward. A white hole, we are inside a region of spacetime from which things can only expand outward, seeded by a singularity in the past. If loop quantum gravity's prediction is correct, if black holes eventually bounce and become white holes, then the obvious question is, what was the singularity of our Big Bang? Was there a black hole on the other side? Was our universe born from the death of a black hole in some other universe? This idea is not entirely without support. Loop quantum cosmology, the application of loop quantum gravity to the universe as a whole, suggests that the Big Bang was not a true beginning but a big bounce. Before the Big Bang, there was a contracting universe that reached a maximum density defined by quantum gravity effects, and then bounced outward into what we experience as the expanding universe we live in. Under this scenario, black holes, white holes, and the universe itself are all part of one continuous cycle. A black hole forms in one universe. It evaporates. At the final moment, it bounces into a white hole. The white hole is the seed of a new universe. That universe expands. Stars form. Some die as supernovas. Some leave behind black holes. And the cycle continues, an eternal recursion of creation and destruction, with each generation of universe seeding the next. This is not established science. The experiments needed to test these ideas are beyond anything we can currently build. But it is remarkable that the mathematics is consistent with it, that nothing in our known physics prohibits this scenario. Black holes began as a mathematical curiosity, a solution to Einstein's equations that seemed too extreme to be real. Within a few decades, they went from theoretical artifacts to observed phenomena. We have now directly imaged them, detected gravitational waves from their mergers, and measured the supermassive black hole at the center of our own galaxy. What started as the most extreme, most destructive objects imaginable has become something more. They are mirrors, objects that reflect back at us the deepest questions about the nature of space, time, matter, and existence itself. Every time we look into them, we find the universe is stranger than we imagined, and we have barely begun to look. Right now, as you're watching this, every single physical process happening around you is obeying a law so fundamental that it essentially defines the direction of time itself. Your coffee is cooling. The air in this room is slowly mixing. The cells in your body are doing things they will never undo. And all of it, every single one of these processes, moves in one direction and never comes back. Most people have never heard a proper explanation for why. And the ones who have, they've almost certainly heard it wrong. I'm talking about entropy. And I promise you, by the end of this video, you will never look at a melting ice cube the same way again. Let's start with the thing everyone gets wrong. Entropy is disorder. You've probably heard this. Teachers say it. Textbooks print it. It gets repeated so often that most people just accept it as fact and move on. The image it creates is vivid. A neat bedroom slowly becoming a mess, a clean desk descending into chaos. Entropy equals things falling apart. Things getting messier. The universe drifting towards chaos. And it sounds intuitive. It sounds right. But it is, in a very specific and important way, completely misleading. And if you keep that definition in your head, you will never actually understand what entropy is or why it matters. Here's a quick test that proves it. Picture a cup of crushed ice, jagged chunks everywhere, random shapes, edges pointing in all directions. Now picture a glass of room temperature water. Smooth, calm, uniform, every molecule in liquid motion. Which one is more disordered? If entropy were really about disorder, the answer would obviously be the crushed ice. It looks messier. It looks more random. Most people say the ice without hesitating, but the ice actually has lower entropy. The water has higher entropy. How does that make sense? If water is calmer, smoother, more uniform, how can it possibly be more disordered? This is exactly why the disorder definition fails us. It creates an intuition that points in the wrong direction. So let's throw it out entirely and replace it with something far more accurate: probability. This is going to take a little more mental effort. But stay with me, because once this clicks, it genuinely changes how you see the world. Let's build everything from scratch. Imagine two tiny solids. We'll call them solid A and solid B. Each one is absurdly simple, just 6 atomic bonds. Think of those bonds like tiny cups sitting in a row. Now imagine that energy, heat energy, comes in small, indivisible packets called quanta. Like coins. You can drop these coins into the cups, but you can't break a coin in half. It either goes in or it doesn't. The more coins, the more quanta a solid has, the hotter it is. That's it. That's the whole model. Now, say we have 8 total quanta of energy split between the two solids. 6 quanta in A, 2 in B. A is the hot one. B is the cold one. Simple enough. But here's where it gets interesting. Those 6 quanta in solid A aren't fixed in place. They can be distributed across the 6 bonds in many different ways. Maybe all 6 quanta pile into one bond. Maybe they spread evenly. Maybe there are 2 in the first bond, 1 in the third, 3 in the fifth. Each unique arrangement of quanta across bonds is called a microstate. And when you actually sit down and count every possible microstate for the configuration of 6 quanta in A, 2 in B, you get 9,702, nearly 10,000 ways to arrange that same energy. Now, what if the energy were distributed differently? What if it were 4 quanta in A and 4 in B, perfectly equal? All 8 in A and none in B. Each different division of energy between the two solids has its own total number of microstates. Here's the single most important idea in this entire video, so pay attention. Every individual microstate is equally likely to occur. The system doesn't prefer any particular arrangement. Every configuration of quanta across bonds, every possible microstate, has exactly the same probability of being the one the system lands on at any given moment. The physics doesn't play favorites. So if every microstate is equally likely, what determines where the system spends most of its time? Simple. Whichever energy configuration has the most microstates. If there are 9,702 ways to have 6 quanta in A and 2 in B, and there are 20,000 ways to have 4 in each, then the system will spend roughly twice as much time in the 4-4 split, not because of any force or preference, but purely because there are more ways for it to be there. And that is entropy. Not disorder. Not chaos. Just this, the number of ways a particular configuration of energy can be arranged. High entropy means many, many microstates, many ways to be in that configuration. Low entropy means few microstates, few ways to land there. That's it. That's the whole concept. In a general sense, what we find is that energy spread out across many particles creates far more microstates than energy concentrated in one place. So high entropy correlates with energy being spread out, and low entropy correlates with energy being bunched up. The disorder intuition comes from this. Spread out things look messier than concentrated things, but the actual cause is the count of microstates, not the visual messiness. Now let's watch this play out dynamically, because this is where entropy stops being a static number and becomes something that explains the flow of time. In reality, energy doesn't sit still. It's constantly jumping between neighboring atomic bonds, billions upon billions of times per second. Every time it jumps, the system ends up in a new microstate. The system is, in a sense, randomly sampling from all its possible microstates, one after another, at an unimaginable speed. So let's go back to our 2 tiny solids. We start with 6 quanta in A and 2 in B. The energy starts bouncing around randomly. As it does, it occasionally moves between the 2 solids. A quantum hops from A to B, or vice versa. Over time, what do we find? We can calculate the probability of where the system will end up. And the numbers are striking. There's a 21% chance that the energy becomes maximally spread out, for quanta in each solid. There's a 13% chance the system returns to exactly where it started, 6 in A, 2 in B. And here's the part that surprises most people. There's an 8% chance that solid A actually gains energy and becomes even hotter than it started. 8%. That's not negligible. With just 12 bonds and 8 quanta of energy, heat has a real, non-trivial chance of flowing the wrong way. The cold solid could spontaneously get colder. The hot solid could spontaneously get hotter. So why does this never happen in real life? Why is it that every single time you set a hot cup of coffee on your desk, it cools down? Never, not once, in the history of humanity, has a cup of coffee sitting on a desk gotten hotter on its own. The answer is one word: scale. Our hypothetical system had 6 bonds per solid. In the real world, even a small object, a marble, a raindrop, a single grain of sand, contains something on the order of 10 squared cubed atoms. That's 100,000 billion atoms. Not thousands, not millions, not billions. A number with 23 zeros after it. Let's scale our thought experiment accordingly. Increase the solids from 6 bonds to 6,000 bonds, and the total energy from 8 quanta to 8,000 quanta. Now recalculate the probability of the hot solid spontaneously gaining energy. The result is a number so small it's almost meaningless to write it down. It's not 1 in a million. It's not 1 in a trillion. It's a decimal point followed by hundreds of zeros before you hit any significant digit. A fraction so astronomically tiny that if you ran this system for the entire age of the universe, all 13.8 billion years of it, the expected number of times this would happen is effectively 0. Not because physics forbids it. Not because there's a rule somewhere that says heat can't flow backward. There is no such rule. Heat can flow backward. It just almost never does, because the ratio of microstates is so unimaginably large in favor of spreading out that the universe never statistically arrives at the alternative. This is the crucial insight that the disorder definition completely hides from you. There is no mysterious force pushing systems toward higher entropy. There is no law saying things must become messier. There is only statistics, and at the scale of real-world objects, those statistics become so overwhelming that we perceive them as ironclad physical laws. Let's make this concrete with the examples you actually encounter every day. Why does ice melt when you put it in a warm drink? Not because warmth overpowers coldness. Not because heat is stronger. It's because liquid water, with all its molecules jostling freely in every direction, has vastly more available microstates than water locked into a rigid crystal lattice. The energy that was ordered and structured in the ice finds an almost infinite number of new configurations available to it once the structure breaks down. From a probability standpoint, the ice simply cannot compete with the overwhelming statistical pull of the liquid state. Why does cream swirl through coffee and never UN swirl? Not because the molecules like being mixed. Not because diffusion is a force that drives things apart. It's because the number of arrangements where cream molecules are clustered together is vanishingly small compared to the number of arrangements where they're spread throughout the cup. If you waited, and I mean really waited, billions of years, watching that cup, the laws of physics technically allow the cream to spontaneously reseparate. But the probability is so close to zero that it has never happened and will never happen within any timescale that has any meaning to us. Why does air rush out of a punctured tire? Because outside the tire, the air molecules have an enormous volume available to them, a whole atmosphere to explore. The number of microstates available to them outside is incomparably larger than the number available inside the constrained volume of the tire. The molecules aren't being pushed out by pressure in any mystical sense. They're simply, randomly, statistically far more likely to be found spread across a large volume than compressed into a small one. In every single case, the pattern is identical. No force.
No intention.
No law saying things must spread out. Just the brute arithmetic of probability, playing out at a scale so large that the outcome becomes a certainty. This is why entropy has been called time's arrow. Think about what time's arrow actually means. You can watch a video of a falling object and then play it backward. The reversed video looks strange, but physically speaking, a ball moving upward from the ground is not impossible. The laws of physics at the microscopic level are time symmetric. They work equally well forwards and backwards. But watch a video of an ice cube melting and play it backward. Suddenly, the water spontaneously refreezes into a perfect ice cube. It looks obviously, immediately, absurdly wrong. Why? Because entropy has been reversed. Because you're watching a process where energy spontaneously concentrates rather than disperses. And your brain, trained by a lifetime of experience in this universe, immediately recognizes that this never happens. The direction of time, what we mean when we say time flows forward, is defined by the direction of increasing entropy. The past is the direction of lower entropy. The future is the direction of higher entropy. The arrow only points one way not because of some metaphysical rule about time, but because the statistics only click in one direction. Once energy spreads out across 10 squared cubed particles, the probability of it spontaneously reconcentrating is so far beneath any practical threshold that for all purposes, it has never happened and never will. The next time you drop an ice cube into your drink and watch it melt, take a moment. You're watching one of the deepest truths about reality play out in a glass. You're watching the reason time moves forward. You're watching the universe explore its microstates, blindly, mechanically, without any purpose or direction, and end up, as it almost always does, in a configuration that is more spread out than before. That's entropy, not disorder, not the universe falling apart. Just probability, staggering, overwhelming, universe-defining probability, playing out at a scale our intuitions weren't built to handle. And if you find that beautiful, good. It is. I want you to hold one number in your mind. 300,000 kilometers per second. That is the speed of light. The absolute speed limit of our universe. No force, no object, no signal can exceed it. And if you're struggling to feel the weight of that number, here's what it actually means in physical space. In 1 single second, a beam of light travels around the entire circumference of the Earth 7 times. Not 7 laps around your block. 7 complete orbits of our planet. In the time it took you to read that sentence, light has already lapped this world several times over. And I need you to sit with that. I need you to actually feel it. Because in about 10 minutes, that extraordinary speed, that cosmic velocity that we as a species have never come close to achieving, is going to seem completely, humiliatingly useless. That same beam of light, moving at 300,000 kilometers every second without pause, without rest, would need 100,000 years to cross our galaxy from one side to the other. 100,000 years. Not to reach another galaxy. Not to traverse some unimaginable intergalactic void. Just to get from one end of our home galaxy, the Milky Way, to the other. Let that land. Because what I'm about to show you is that this fact, this already mind-bending fact, is merely the opening sentence of a story so vast it will fundamentally rewrite how you see your place in existence. We are going to zoom out, step by step, until the numbers stop being numbers and start being something closer to philosophy. And then, at the very end, I'm going to flip the entire thing on its head. Because there is a twist. And it changes everything. Let's start with what we are actually proud of. In 1977, humanity launched 2 spacecraft into the void. Voyager 1 and Voyager 2, twin emissaries from Earth, sent to survey the outer planets and then keep going. Today, Voyager 1 holds the record as the fastest and farthest human-made object in history. It is screaming through space at approximately 17 kilometers per second. That's over 61,000 kilometers per hour. A speed so fast that if you could drive a car at that velocity, you'd circle the Earth in under 40 minutes. NASA talks about Voyager 1 with a certain reverence. And honestly, why wouldn't they? The fact that we built something in the 1970s that is still functioning, still transmitting data, still reaching us across the darkness, it's genuinely one of humanity's greatest engineering achievements. But here's what we don't say out loud very often. After 47 years of continuous travel at that extraordinary speed, Voyager 1 has covered roughly 24 billion kilometers. That sounds enormous. That sounds like a triumph. And then you do the math in cosmic units, and the triumph quietly evaporates. 24 billion kilometers is approximately 22 light hours. Not light years. Light hours. Meaning that the distance Voyager has traveled in nearly half a century is a distance light crosses in under a single day. If Voyager 1 maintained its current speed, which it can't because it will eventually run out of power, and aimed itself directly at Proxima Centauri, the very nearest star to our Sun, it would arrive in approximately 73,000 years. 73,000 years ago, anatomically modern humans were just beginning to spread out of Africa. There were no cities, no writing,
no agriculture.
The entirety of human civilization, from its earliest mud brick foundations to the phone in your pocket, fits inside a span of time that is still less than what it would take our fastest spacecraft to reach our nearest stellar neighbor. We have not left our neighborhood. We have barely stepped off our front porch. The cosmic era of human exploration, the thing we celebrate with launch countdowns and mission patches and the word astronaut, it is, in galactic terms, indistinguishable from standing still. And Proxima Centauri, let's be clear, is not some distant exotic destination. It's the next house on the street. It's practically touching us. Beyond it lies a galaxy of 200 to 400 billion other stars, and we can't reach even the closest one in any meaningful human timeframe. So that is our starting position. Earth. One small planet. And a civilization that is, cosmically speaking, going absolutely nowhere. Now let's talk about our galaxy. Because even after you absorb the Voyager reality check, the Milky Way still sounds impressive. We live in a spiral galaxy. It has hundreds of billions of stars. It has a supermassive black hole at its center. It has complex structure, stellar nurseries, ancient globular clusters, dark lanes of interstellar dust. It is, by every human measure, stupendously large and stupendously complex. Let me give you a number to anchor its scale. If you wanted to count every star in the Milky Way, if you sat down and counted one star per second, without sleeping, without stopping, it would take you somewhere between 6,000 and 12,000 years to finish. More than all of recorded human history, just to count the stars in our own galaxy one by one. That's the Milky Way. Our galaxy. The thing we call home. Now meet IC 1101. IC 1101 is a galaxy located about 1 billion light-years from Earth. And it is not a normal galaxy. It is the largest galaxy currently known to science. While the Milky Way spans roughly 100,000 light-years across, IC 1101 stretches across approximately 6 million light-years. It contains an estimated 100 trillion stars, somewhere between 250 and 500 times more than our entire galaxy. But raw numbers can be abstract, so let's make this physical. Let's run a thought experiment. Take IC 1101 and place it exactly where the Milky Way sits right now. Center it on our position. Let it expand outward the way it actually exists in space. The Milky Way would be swallowed instantly. That's obvious. But here's what's less obvious. The Andromeda Galaxy, our nearest large galactic neighbor, sits about 2.5 million light-years away from us. IC 1101 would swallow Andromeda too. It would engulf the entire local group, the cluster of roughly 50 galaxies that the Milky Way and Andromeda both belong to. All of them. Gone. Absorbed into a single structure that, from the outside, would look like one enormous, glowing, roughly spherical blob of ancient stars. IC 1101 isn't a galaxy in the way we typically imagine galaxies. Dynamic, spiraling, youthful. It's an elliptical galaxy, ancient and bloated, the gravitational graveyard of countless smaller galaxies it has consumed over billions of years. It sits at the center of a massive galaxy cluster, feeding and growing and simply existing on a scale that makes our home look like a single grain of rice dropped on a football field. And here is the thing that I really need you to feel. IC 1101 is not the universe. It's not even a meaningful fraction of the universe. It is one data point, one structure among billions. The universe doesn't stop at IC 1101, not even slightly. To understand what actually exists out there, you need to understand how structure works at the largest scales. Because the universe is not a uniform fog of evenly distributed galaxies. It has architecture. It has a skeleton. And when you see that skeleton, something in your spatial intuition simply breaks. Individual galaxies, even enormous ones like IC 1101, are not isolated. Gravity binds them together into clusters. Clusters are bound into superclusters. And superclusters are connected by enormous filaments of dark matter and gas, vast cosmic highways that stretch across hundreds of millions of light-years, into a structure that astronomers call the cosmic web. Start with our own position in this web. The Milky Way belongs to the local group. About 50 galaxies, held together by mutual gravity, spread across a volume roughly 10 million light-years across. In the context of what's coming, this is an almost invisibly small dot. The local group is itself part of a larger structure, the Virgo supercluster. This supercluster contains hundreds of galaxy groups and clusters, sprawled across a region approximately 110 million light-years wide. For decades, astronomers considered this one of the largest coherent structures in the observable universe. Then, in 2014, a team led by astronomer Brent Tully at the University of Hawaii published a paper that redrew the map. They introduced us to Laniakea. The name comes from the Hawaiian language and means immeasurable heaven. And the name is not an exaggeration. Laniakea is a supercluster of superclusters, a vast gravitational basin that encompasses the entire Virgo supercluster as just one small component. It contains an estimated 100,000 large galaxies. It spans roughly 520 million light-years in its widest dimension, and it has a total mass equivalent to approximately 100 million billion times the mass of our Sun. The Milky Way sits near the outer edge of Laniakea, like a small town on the fringes of an unimaginably vast metropolitan region whose center we will never reach, whose extent we can barely map, and whose existence we only recently discovered. Let me build the chain for you, step by step, so you can feel each link snap into place. You are here, on a planet roughly 12,700 kilometers across. That planet orbits an ordinary star, not a particularly large star, not a particularly bright star, just one of the unremarkable middle-aged yellow stars that the galaxy produces in enormous quantities. That star sits about 26,000 light-years from the center of the Milky Way, somewhere in a region called the Orion Arm, a minor spiral arm of a mid-sized spiral galaxy. Not at the center. Not in a particularly special location. Just out there, in the suburbs of a structure containing several hundred billion other stars. That galaxy, the Milky Way, is one of roughly 50 galaxies in the local group. The local group is one component of the Virgo supercluster. The Virgo supercluster is one of the smaller lobes of Laniakea. And Laniakea is one of an estimated 10 million similar superclusters in the observable universe. 10 million. At each step, you are not simply getting bigger. You are watching everything you previously understood as large become negligible. The planet becomes a mote of dust in the solar system. The solar system becomes a pinpoint in the galaxy. The galaxy becomes a dim speck within the supercluster. And the supercluster itself becomes an almost imperceptible point within the greater architecture of everything. By the time you are standing at the scale of the observable universe, looking at all of it, all 93 billion light-years of its diameter, all its billions of galaxies arranged in their vast filaments and voids, Laniakea is barely visible. And you, sitting on your planet, in your solar system, in your galaxy, in your local group, in your supercluster, in your corner of everything. You are not a rounding error. You are below the resolution of the image. Now I need to tell you something that makes all of this worse. That observable universe I just mentioned, it is not the same as the actual universe. And the distinction matters enormously. When astronomers use the phrase observable universe, they are not saying everything we've managed to see so far with our best telescopes. They are not describing a technological limitation, a horizon that will expand as we build bigger instruments and send them farther from Earth. The observable universe is a hard physical boundary, a wall built not from matter but from the nature of spacetime itself. Here is why. The universe is expanding. This is not controversial. It's one of the most well-supported facts in all of cosmology, confirmed by multiple independent lines of evidence. Galaxies are not flying apart through space like debris from an explosion. Space itself is expanding. The fabric of the cosmos is stretching. And critically, there is no speed limit on how fast space can expand. The speed of light limits how fast things can move through space. It says nothing about the space itself. At very large distances, the expansion of space is fast enough that distant regions are moving away from us faster than light can travel through the intervening distance. This means that light from those regions will never reach us. Not because it's been blocked. Not because the universe has a wall. But because the space between us and those sources is expanding faster than light can cross it. The observable universe is simply the sphere within which light has had enough time, since the Big Bang, to reach our position. Its edge is called the cosmological horizon. And that edge is not static. Every second, galaxies that were previously reachable, galaxies from which light was, in principle, heading toward us, cross that threshold. Their light redshifts, stretches, and fades. Eventually, it never arrives. Think about what that actually means. Right now, at this moment, while you are watching this video, thousands of galaxies are permanently crossing the boundary beyond which we will never see them. They are not being destroyed. They still exist. They may contain stars, planets, and for all we know, civilizations of their own. But the fabric of space is pulling them away faster than information can travel, and they are slipping behind a curtain that will never be lifted. The universe is not only unimaginably large, it is actively hiding itself from us. It is, in real time, closing off rooms and sealing doors and making itself less knowable by the second. This is not science fiction. This is a straightforward consequence of the physics we understand best. And it means that the observable universe, already a structure so large that the numbers describing it cease to feel like numbers, is itself only a small, finite window into something even more vast, something we can never fully map, something that may be effectively infinite. At some point in the past several minutes, a rational person would be forgiven for feeling something close to despair. After all, consider what the mathematics tells us. Consider what the numbers say about our significance. You are a biological organism living on a rock roughly 12,700 kilometers in diameter. That rock orbits a star that is, to put it charitably, average in every measurable way. That star is one of perhaps 400 billion in a galaxy that, when placed next to IC 1101, looks like a dust grain next to a boulder. That galaxy is a peripheral member of a small galactic group, which is one lobe of a supercluster, which is one of millions of similar structures spread across a cosmos so large that the speed of light, the fastest anything can ever move, becomes a crawl, a shuffle, a slow trudge through an incomprehensibly deep space. The numbers say, plainly and without sentiment, that you are less than negligible. They say that the matter composing your body, the electrical signals firing through your neurons at this very moment, the brief flicker of consciousness that is your life, all of it, in the language of cosmic scale, rounds down to zero. A rounding error in an equation that doesn't know you exist. This is what the universe looks like through pure mathematics. And I've been building toward this conclusion deliberately, because I want you to feel its full weight before I tell you why I think it's completely wrong. Here is the thing about IC 1101. That galaxy, with its 100 trillion stars and its billions of years of accumulated mass and its position at the center of a massive galaxy cluster, it has never had a thought. Not one. In all its vast, glowing, incomprehensible existence, not a single moment of awareness has arisen within it. It processes nothing. It knows nothing. It has absorbed dozens of smaller galaxies over cosmic time and registered none of it. It simply exists, enormous and entirely blind. The Laniakea supercluster, 100,000 galaxies, 520 million light-years across, inconceivable mass, has never experienced curiosity. It has never asked a question. The filaments of the cosmic web, those vast dark matter highways stretching across hundreds of millions of light years, have never looked at themselves and wondered what they are. Dark matter, which makes up roughly 27% of the universe's total energy content, cannot reflect. It has no interior life. It bends light and shapes structure and is utterly, permanently unconscious. The universe, for all its staggering material abundance, is almost entirely dark. Not just in the optical sense, in the experimental sense. Incomprehensibly vast quantities of matter and energy, organized into breathtaking structures, unfolding across billions of years, and almost none of it has ever seen itself. Almost none of it has ever been seen at all. And then there is this planet. This small, unremarkable, cosmically insignificant rock, orbiting its unremarkable star, in its unremarkable position in the outer arm of an average galaxy. On this planet, 4 billion years of chemistry and chance and catastrophe and evolutionary pressure produced something that had never existed anywhere in the observable universe before, at least not that we can confirm: awareness, consciousness, the ability of matter to become curious about itself. You are, as far as we know, the universe's only mechanism for self-reflection. When you look up at the night sky, the universe is not simply being observed. For those few seconds, the universe is observing itself through you. When you process the information in this video, when you feel the scale begin to click into place, when something in your mind shifts as you try to absorb the distances and the numbers, that shift, that process of comprehension, is not happening in a vacuum. It is happening inside a cosmos that, without minds like yours, would continue to expand and contract and burn and cool and never once know that any of it was occurring. The stars in IC 1101 will shine for billions of years without any of that energy ever being converted into understanding. The filaments of Laniakea will persist for cosmic timescales without producing a single moment of experience. The observable universe will expand and cool and eventually dim toward heat death, and if consciousness like ours disappears before then, all of it, all 93 billion light-years, all the billions of galaxies, all the dark matter and dark energy and ancient light, will end having been fundamentally unwitnessed. You are not lost in the scale. You are the scale's only audience. I want to be careful here, because I'm not making a claim about cosmic purpose. I'm not saying the universe was designed to produce observers, or that human beings occupy some special metaphysical position. The evidence doesn't support that, and intellectual honesty matters too much to reach for comfortable conclusions. What I am saying is something more specific and, I think, more interesting. The universe's material dominance over you is total and absolute. There is no scale at which your physical size competes with its size, your lifespan with its age, your energy with its energy. In every material comparison, you lose by a margin so overwhelming that losing doesn't quite capture it. You are simply not in the same category. But there is one thing, and as far as we know, it is only one thing, that the universe cannot do for itself. It cannot turn around and look. It cannot hold a fact in mind and interrogate it. It cannot feel the strange, vertiginous sensation of recognizing its own vastness and being undone by that recognition. The fact that you can feel something right now, some version of awe or insignificance or wonder, that feeling is not nothing. That feeling is, in a very real sense, the universe's most improbable achievement. The emergence of complexity sufficient to become self-aware is not a foregone conclusion of physical law. It is extraordinarily rare, potentially unique, and it happened to produce you. Every number I've given you tonight is real. The speed of light. Voyager's 73,000-year journey to Proxima Centauri. The 100,000 light-year width of the Milky Way. IC 1101's 6 million light-year diameter. Laniakea's 520 million light-years. The 10 million superclusters in the observable universe. The galaxies crossing the cosmological horizon right now, slipping forever beyond our reach. All of those numbers are accurate, and they all point in the same direction. The universe is ancient and enormous and indifferent. It will persist long after you are gone. It was here long before you arrived. On any physical scale, you do not register. But the universe has been unfolding for 13.8 billion years without being understood. Galaxies have been born and died without being named. Light has traveled for billions of years without being received by any conscious mind. The entire performance has been happening in an empty theater, or almost empty. And you walked in. Maybe that's not consolation. Maybe knowing that you are the universe's improbable instrument of self-examination doesn't make the numbers smaller or the distances less lonely. Maybe the vertigo remains. That's fine. It should remain. A cosmos this large deserves to leave you a little breathless. But before you close out this video and return to your day, to its ordinary scale, its human proportions, its familiar geography of rooms and streets and faces, I want you to carry one thought. Somewhere in the Laniakea supercluster, in the outer arm of a mid-sized spiral galaxy, on the third planet of an unremarkable star, a collection of atoms arranged itself into something capable of looking at the universe and feeling small. The universe has been doing extraordinary things for 13.8 billion years. That might be the most extraordinary thing it's ever done. Dark matter, the invisible substance that makes up 85% of everything that has mass in this universe, and that modern science still cannot identify. Hasn't gotten around to identifying yet. Cannot. Right now, as you're watching this, that substance is passing through the screen in front of you, through the walls of the room you're sitting in, through your own body, completely undetected, leaving no mark, no resistance, no trace. And nobody on Earth can tell you what it is. Here's the part that should really unsettle you. Everything you have ever seen with a telescope, every star, every planet, every glowing nebula, every one of the hundreds of billions of galaxies scattered across the observable universe, adds up to about 5% of the total mass and energy that actually exists. 5%. The stars in the night sky, the ground under your feet, your own body, the entire visible cosmos that humanity has spent thousands of years studying, mapping, and photographing, is a thin coat of paint on top of something vastly larger that we simply cannot see. We gave that hidden majority a name, dark matter. But a name is not an explanation. It's a placeholder for one of the biggest blank spots in modern science. So let's actually go looking for it. Not in some abstract, philosophical way. Let's follow the exact trail of evidence that forced physicists, kicking and screaming, to accept that something invisible has to exist. Because nobody wanted this conclusion. Scientists don't enjoy admitting that 85% of the universe is a mystery. They were pushed into that admission by an equation that simply refused to balance. Here's a promise before we get into it. Everything in this video is built on real, published, peer-reviewed evidence. The same kind of evidence that put rovers on Mars and confirmed gravitational waves. Nothing here is speculation dressed up as fact. What makes dark matter so gripping isn't that it's a fringe theory. It's that it's the mainstream, heavily tested conclusion of modern cosmology, and it still leaves us with a universe that is, at its core, mostly unidentified. The story starts with something you can actually picture, a spinning galaxy. Take our own galaxy, the Milky Way, or any of the hundreds of billions like it scattered across space, vast, flattened disks of stars, gas, and dust, all rotating slowly around a common center, the same way water swirls around a drain, just on a scale that makes vast feel like an understatement. Basic physics tells you exactly how something like that should behave. Near the crowded, mass-heavy center of a galaxy, stars should whip around at high speed, held in place by strong gravity from all that concentrated material nearby. Out at the sparse, mostly empty edges, where there's much less visible mass to hold anything in place, stars should slow down. That's not a guess. That's the same orbital mechanics that governs the planets in our own solar system. Mercury, close to the Sun's overwhelming gravity, screams around its orbit in just 88 days, while distant Neptune, far from that gravitational pull, takes a leisurely 165 years to complete a single lap. Closer and faster near the mass, farther and slower away from it. Simple. Reliable. It's worked for every solar system model ever built. Now point that same physics at a galaxy, and it breaks. In the 1970s, an astronomer named Vera Rubin carefully measured the rotation speeds of stars at different distances from the centers of spiral galaxies, expecting to confirm exactly what the equations predicted, a steady drop-off in speed as you move outward, matching the drop-off in visible matter. Instead, she found something that shouldn't have been possible. The stars at the outer edges of these galaxies, way out past most of the visible stars and glowing gas, were moving just as fast, in many cases, as the stars much closer to the center. The rotation curve was flat. It stayed flat, far out into regions where the maps of visible matter said there was almost nothing left to hold anything in place. Think about what that actually means physically. A star orbiting that far out, moving that fast, based on the gravity supplied by only the visible matter in the galaxy, should be flung outward, torn away from the galaxy entirely, the same way a rock on a string flies off if you swing it too fast for the string to hold. According to the visible mass alone, spiral galaxies across the universe should be actively, continuously flying apart, stars scattering into intergalactic space in every direction. They are not. They have held their shape, stable and intact, for billions of years. There is a direct, glaring contradiction between what the math says should happen and what every telescope on Earth had exactly two options, and both of them were radical. Option 1. Our understanding of gravity itself, built on Newton and refined by Einstein, tested across a century of experiments and successfully used to land spacecraft on other planets, is somehow fundamentally wrong at galactic scales. Option 2. There is a massive amount of additional matter in and around every galaxy that we simply cannot see, matter that contributes gravity but emits no light, providing the extra gravitational muscle needed to keep those fast-moving outer stars locked in orbit instead of flying off into the void. The overwhelming majority of evidence gathered since Rubin's original measurements points toward option 2. Somewhere out there, wrapped around every single galaxy like an invisible skeleton, is enough extra mass to change the entire outcome of the story, and we cannot see a single particle of it. If that were the only piece of evidence, you might reasonably stay skeptical. One anomaly, one measurement, one clever workaround. But it isn't the only piece of evidence. It's just the first domino. And once you start pulling on this thread, it runs through nearly every corner of modern astrophysics, showing up again and again in places that have nothing obviously to do with spinning galaxies. Let's talk about what this invisible material actually is, or rather, what it definitely is not, because ruling things out is how physicists have cornered this mystery. Start with the obvious guess. Maybe dark matter is just ordinary matter that happens to be dark. Cold planets that never ignited into stars, dim burnt-out stellar corpses, rogue asteroids, and dust clouds drifting unlit through interstellar space, black holes that swallow every photon that gets near them. Surely the universe is full of ordinary stuff we simply failed to spot with a telescope. This was actually the leading hypothesis for years, and it has a real name: massive compact halo objects, or MACHOs for short. Astronomers went looking for them using a clever trick, watching for the way a dark, massive object passing in front of a distant star would briefly bend and brighten that star's light through gravity, like a lens flashing across the sky. They found some. Not nearly enough. The numbers don't come close to covering the missing mass. Whatever's out there, it is not simply made of unlit versions of the ordinary matter we already know. That leaves something far stranger. Dark matter appears to be built from a type of particle that doesn't exist anywhere in the standard model of particle physics, the enormously successful framework that already accounts for every electron, proton, quark, and photon ever detected in a laboratory. Whatever dark matter is made of, it does not interact with light in any way. It doesn't absorb photons. It doesn't emit them. It doesn't reflect them, scatter them, or block them. You could stand in a beam of pure dark matter and it would pass directly through your body as if you weren't there at all, and you'd never see so much as a shimmer, because there's no electromagnetic interaction happening whatsoever. That single missing property is what makes it dark in the first place. Not black, not merely dim, but genuinely, totally transparent to every form of light in the electromagnetic spectrum, from radio waves to gamma rays. It gets stranger still. Dark matter doesn't appear to be made of protons or neutrons either, meaning it isn't built from the same fundamental particles that make up atoms, and therefore isn't built from atoms at all, in any conventional sense of that word. It has mass, and that mass produces gravity, exactly like ordinary matter. But it does not clump together, collide, or interact through anything except gravity itself. Two ordinary atoms bump into each other constantly. That resistance, that solidity, is the reason your hand doesn't pass through a table. Dark matter has no equivalent to that resistance. Two particles of dark matter can apparently pass straight through each other, and straight through you, without so much as a nudge. It occupies the same space as ordinary matter and simply ignores it, the way a ghost in an old movie walks through a wall without disturbing. Once you strip away everything dark matter is not, a form of matter that has mass, that generates gravity, and only gravity, that does not shine, reflect, absorb, collide, or clump the way ordinary particles do. In a very real sense, dark matter behaves like matter's gravitational shadow, all of the pull, none of the presence. It is the single thread connecting our familiar universe to something built out of entirely unfamiliar rules, a substance that participates in exactly one of nature's four fundamental forces and stays a ghost with respect to all the rest. And here's the detail that should really stop you. This impossible ghost substance outweighs everything we can actually see and touch by more than 5 to 1. Take a moment to picture your own body in that light. Right now, Trillions of dark matter particles, if the leading models are correct, are streaming through you every single second, entering through your chest and exiting through your back without depositing so much as a flicker of energy, without triggering a single nerve, without leaving any trace that a physicist could measure. You have spent your entire life submerged in an invisible current that outweighs the visible universe 5-to-1, and you have never once felt it, because feeling it would require exactly the kind of interaction this substance seems constitutionally incapable of having. You'd think a phenomenon this strange, this invisible, would be a footnote in cosmic history, background noise, irrelevant to the bigger picture. It's the opposite. It turns out this invisible scaffolding isn't just holding galaxies together today. It built them in the first place. Without it, none of this, the stars, the planets, the very ground you're standing on, would exist at all. Rewind the clock back to the very early universe, not long after the Big Bang. At that stage, ordinary matter existed almost entirely as an extremely hot, extremely energetic gas, mostly hydrogen and helium, spread out nearly uniformly across all of space, moving far too fast and too chaotically to settle down and clump into anything. Gravity needs time and stillness to pull matter together into dense structures like stars and galaxies, and a violently hot, fast-moving gas resists exactly that kind of settling. Left entirely to itself, ordinary matter in that state would have stayed smooth and diffuse for a very long time, struggling to form the seeds of the structures we see today. Dark matter had no such problem. Because it doesn't interact with light or radiation pressure the way ordinary matter does, it was able to start clumping together under its own gravity far earlier, completely unbothered by the intense heat and radiation filling the young universe. While ordinary matter was still being buffeted and kept smooth by that early cosmic fireball, dark matter was quietly forming a vast, invisible web of gravitational wells, dense knots and filaments spread across the young cosmos, completely undetectable, but already exerting a powerful gravitational pull on everything around them. That invisible scaffolding became the blueprint for the entire visible universe. As the cosmos expanded and cooled, ordinary matter, that hot hydrogen and helium gas, began falling into the gravity wells that dark matter had already carved out, the way rainwater runs downhill into valleys that were shaped long before the rain arrived. Gas collected inside those dark matter clumps, compressed under gravity, heated up, and eventually ignited into the first generation of stars. Those stars clustered together inside the largest dark matter concentrations and became the first galaxies. Everything about the large-scale structure of the universe today, the way galaxies cluster together in enormous chains and sheets, separated by vast empty voids, forming a shape astronomers genuinely call the cosmic web, traces directly back to that early, invisible dark matter scaffolding. Run a computer simulation of the universe using only ordinary matter and ordinary gravity, without dark matter included, and you get a universe that doesn't look anything like ours. Fewer galaxies, structures that form far too late, a cosmos that doesn't match what telescopes actually show us. Add dark matter back into the simulation, and the structure snaps into place, matching real observations that terrified physicists as an unexplainable anomaly turned out to be the universe's original architect. Without that invisible gravitational skeleton forming first, gas would have stayed too smooth, too spread out, for stars to ever ignite, for galaxies to ever take shape, for planets to ever condense out of stellar debris. No dark matter means no galaxies. No galaxies means no stars like our sun. No sun means no Earth, no chemistry, no life, no you. The substance that makes zero physical contact with anything you can touch is, indirectly, the reason there's anything here to touch at all. Which brings us to the part of the story happening right now, in laboratories and observatories around the world, the actual hunt for this thing. Because knowing dark matter exists, through its gravitational fingerprints scattered across the cosmos, is a very different problem from actually catching a piece of it, and that second problem remains stubbornly, famously unsolved. One of the most striking pieces of evidence comes from something called gravitational lensing, and it turns entire galaxy clusters into enormous, accidental telescopes. According to general relativity, mass doesn't just create gravity in the everyday sense, it actually bends the fabric of space itself, and light traveling through bent space follows that curve, the same way a marble rolling across a warped sheet curves around a dip instead of going straight. When light from an extremely distant galaxy passes near a massive foreground galaxy cluster on its way to us, the immense gravity of that cluster bends the light's path, distorting, smearing, and sometimes even duplicating the image of that background galaxy into strange arcs and rings. Astronomers can measure exactly how much that light has been bent and warped, and from that measurement, calculate precisely how much mass the foreground cluster must contain to bend light by that amount. Here's the key result. When astronomers compare that calculated mass, the true gravitational mass, revealed by the bending of light, against the mass of everything visible in that cluster, the stars, the gas, the glowing material you can actually photograph, the numbers don't come close to matching. The lensing consistently reveals 5, 6, sometimes closer to 10 times more mass than the visible material can account for. Space itself is being warped by something the cameras simply cannot photograph. One of the most dramatic confirmations of this came from a system called the Bullet Cluster, two massive clusters of galaxies that collided, where the visible gas, superheated and slowed by the collision, ended up in one location, while gravitational lensing maps showed the bulk of the mass had sailed straight through, completely unaffected, exactly the way you'd expect if that mass barely interacts with anything except gravity. It remains one of the cleanest, most direct pieces of observational proof that dark matter is real, and that it is genuinely separate from ordinary matter. Lensing tells you dark matter is out there and roughly how much of it exists. It does not tell you what it actually is, down at the particle level. For that answer, scientists have to try something far more difficult, catching a single dark matter particle in the act of physically colliding with an atom of ordinary matter, here on Earth, even though every property we've discussed suggests that collision should be almost unbelievably rare. This is where the story shifts from telescopes pointed at the sky to instruments buried deep underground, and the depth isn't incidental, it's the entire point. Several of the most sensitive dark matter detectors on the planet sit at the bottom of old mines, more than a kilometer beneath solid rock, in places like the Gran Sasso Laboratory tunneled into an Italian mountain, or the Sanford Underground Research Facility inside a former gold mine in South Dakota. All that rock overhead isn't there to hide from dark matter. Dark matter would pass through a mountain as easily as it passes through empty air. The rock is there to block cosmic rays and other ordinary radiation constantly raining down from space, noise that would otherwise drown out the impossibly faint signal. Scientists laboratories sit tanks containing many tons of ultra-pure liquid xenon, chilled and shielded with extraordinary care, sitting in near-perfect silence and darkness, waiting. The logic is almost unbearably patient. If dark matter particles really are streaming through the Earth constantly, then occasionally, extremely rarely, one of them should strike the nucleus of a xenon atom head-on, causing that atom to recoil very slightly and release a tiny, specific flash of light and charge. Detect that exact signature, ruling out every other possible cause, and you've caught direct evidence of a dark matter particle interacting with ordinary matter for the very first time in human history. Teams of scientists have run these detectors continuously for years, watching, waiting, filtering out every possible false signal, and so far, nothing. Not one confirmed direct detection. Every run adds valuable information by narrowing down what dark matter cannot be, tightening the range of possible particle masses and interaction strengths, but the particle itself continues to slip through every trap set for it, exactly as its properties predicted it would. That's genuinely where things stand today. Not a settled textbook chapter, but an active, ongoing hunt, playing out in real time, in tunnels beneath mountains and in observatories aimed at colliding galaxy clusters. Multiple experiments across the globe are racing to be the first to catch a direct signal, refine the particle physics models, and finally answer the question that has been sitting, unresolved, at the center of cosmology for half a century. Nobody currently working on this problem knows for certain how it ends. It's entirely possible that within your lifetime, some detector deep underground will finally record that one impossibly rare flash of light, and dark matter will stop being a placeholder name for an unsolved mystery and become an actual, catalogued particle with a mass and a set of known properties. Or it's possible the mystery deepens further, and the true answer turns out to be even stranger than a new particle. Nobody knows which outcome is coming, and that uncertainty is precisely what makes this one of the most genuinely open frontiers left in modern physics. It's worth saying plainly, this isn't a story with a neat resolution yet, and that's exactly why it's worth paying attention to right now, rather than waiting for the textbooks to catch up. Every few years, a new detector comes online with greater sensitivity than the last. A new galaxy survey maps the cosmic web in finer detail. A new simulation tests the leading models against reality with sharper precision. Somewhere in a lab right now, a physicist is staring at a screen, watching for a flash of light in a tank of liquid xenon that may never come, or may come tomorrow. That's not a metaphor for scientific progress in general. That's a literal, ongoing experiment, happening on this exact day, aimed at answering the biggest open question in the story of the universe's composition. Step back now and look at the full shape of everything we've just walked through. Every star you have ever wished on. Every planet ever photographed by a passing spacecraft. Every galaxy captured in every deep field image ever released by a space telescope, scattered by the hundreds of billions across the observable universe. All of it, all of that light, all of that structure, all of that visible grandeur, is a rounding error. A thin, glowing film stretched across the surface of something enormously larger, older, and more fundamental that remains completely invisible to every instrument humanity has ever built. The universe you can see is not the main event. It's the exception. The overwhelming majority of everything that exists doesn't shine, doesn't burn, doesn't reflect a single photon back at your eyes or your telescopes, and yet it is the very thing holding the visible portion together, the scaffolding that gathered ordinary gas into the first stars, that shaped galaxies into the sweeping spiral patterns you've seen in 1,000 photographs, that keeps those same galaxies from tearing themselves apart to this very day. We are, in the most literal sense possible, living inside a structure built by something we cannot detect, made of something we cannot name, using rules we do not yet shift worth sitting with. We tend to think of ourselves as living inside the universe, the stars, the planets, the galaxies, the whole grand visible tapestry stretched across the night sky. In reality, we are living inside a small, unusual, brightly lit exception, a thin visible layer resting on top of a vast, silent, invisible ocean that outweighs it more than 5 to 1. Every question you've ever asked about the cosmos, every equation ever written to describe it, has so far only managed to describe about 5% of what's actually there. The rest is still out there, right now, moving through this room, waiting for someone to finally figure out what it is. Think about that the next time you look up at a clear night sky and feel like you're seeing the universe laid out in front of you. You're not. You're seeing a faint, glowing outline traced onto something much bigger and much darker, the same way a handful of streetlights might trace the shape of a city at night without showing you a single building, a single street, a single person living inside it. Every star is a landmark sitting on top of an invisible foundation. Every galaxy is a lit window in a structure whose true size we are only beginning to guess at. The universe was never mostly the part we could see. It just took us until fairly recently to realize how badly that assumption was wrong, and it may take a great deal longer to find out exactly what fills in the rest. Black holes are real. We have photographed them. We know they exist, swallowing stars, tearing planets apart, crushing entire solar systems into points smaller than an atom. That part is not in question. But here is the part almost nobody tells you. The same math that proves black holes exist also proves something else can exist. Something that does the exact opposite job. Something that cannot pull anything in, no matter how hard you try to push it there. Something that only pushes out, forever. It has a name. Scientists call it a white hole. And once you understand what it actually is, you will never look at a black hole the same way again. Here is the wild part. This is not science fiction. This is not a fringe theory some random YouTuber made up for views. If a black hole is the ultimate cosmic drain, an abyss that consumes everything that dares to cross its border, the equations say there has to exist a cosmic fountain somewhere too, a place where matter, light, and energy erupt outward without end, and where nothing, absolutely nothing, is ever allowed to enter. Total hunger on one side. Total refusal on the other. Two absolute opposites, sitting inside the exact same set of equations. So what happens when you slam them together? Stay with me until the end, because you are about to find out why some of the sharpest physicists alive today believe every black hole in existence, including the monster sitting at the center of our own galaxy right now, is secretly getting ready to become something else entirely. Before we go any further, ask yourself something. If these two objects are perfect opposites of each other in the math, and one of them is sitting quietly at the center of nearly every galaxy in the universe, including our own, why has almost nobody outside of physics ever heard the other one mentioned by name? Is it because it is simply too rare to matter? Or is it because the truth about it is stranger, and far more unsettling, than most people are ever told? Keep that question in your back pocket. We are going to answer it before this video ends. Let's start with the monster you already think you understand. A black hole is usually described as an object, but that description barely scratches the surface. It is better understood as a one-way street carved directly into the geometry of reality. Once you cross a certain invisible line, there is no version of physics, no amount of thrust, no clever trick, no exotic technology that lets you turn around and go back. That line is called the event horizon, and it might be the single most absolute boundary that exists anywhere in nature. Think for a moment about what it actually takes to escape a planet's gravity. Earth has what scientists call an escape velocity, the exact speed an object needs to break completely free of the planet's pull. For Earth, that number sits at roughly 11 kilometers per second. Leave our planet behind and try to escape the gravity of the Sun itself, and that number jumps to around 618 kilometers per second. Big numbers, but not impossible ones. Now cross the event horizon of a black hole, and the escape velocity required does not simply climb higher. It rockets past the speed of light itself, 300,000 kilometers every single second, the fastest speed anything can ever travel in this universe. Once escaping requires exceeding the cosmic speed limit, escape stops being difficult. It becomes mathematically, physically, permanently impossible. Now picture exactly what falls into that boundary, day after day, for billions of years. Entire stars, some 10, 20, even 50 times more massive than our own sun, get pulled in and shredded apart by tidal forces so extreme they would stretch a human body into a thread thinner than spaghetti, a process astrophysicists have actually nicknamed spaghettification. Whole planetary systems, gas clouds spanning distances of trillions of kilometers, entire pockets of the galaxy, get slowly funneled down into a single, unthinkable point smaller than an atom. This point is called a singularity, a place where our current laws of physics simply break down, where density becomes infinite, and where space and time themselves stop behaving the way they do everywhere else in the universe. A black hole, in every meaningful sense, is the most perfectly engineered vacuum in existence. It has exactly one function, and it performs that single function with terrifying, flawless efficiency. Pull everything toward the center. Let absolutely nothing leave. This is the baseline. This is the villain everyone already fears, the one whose photograph made headlines around the entire planet, that glowing, fiery ring of light wrapped around a circle of total darkness. Keep this image locked firmly in your mind, because we are about to take everything you just learned and turn it completely inside out. And before you assume you already understand exactly what a black hole is capable of, consider this. Not even light can escape one, which means, in a very real sense, a black hole is not simply dark. It is the one place in the entire universe where the concept of seeing inside stops meaning anything at all. Every photon, every particle of light that has ever tried to carry information back out from beyond that horizon, has failed every single time, without exception, for as long as black holes have existed. That is the level of totality we are dealing with. Now hold on to that thought, because the object we are about to introduce breaks that totality in the most complete way physics allows. Now flip every single detail you just heard, one by one, and you begin to understand an object that most people have never even heard mentioned. Imagine something with an event horizon, just like a black hole has, but with one twist that flips the entire concept on its head. Instead of a boundary you can cross going in but never crossing going out, imagine a boundary you can never cross going in, but one that constantly, endlessly, violently ejects everything from inside it, outward, forever. And here is where things get genuinely strange. Even if you were somehow moving at the speed of light itself, the fastest velocity permitted anywhere in this universe, the space surrounding a white hole would still push you away with infinite force before you ever got close enough to touch it. You cannot fall into a white hole. You cannot approach a white hole. You cannot make contact with a white hole under any circumstance the laws of physics allow. Space itself, in the immediate neighborhood of a white hole, behaves like an invisible wall made entirely out of outward pressure, a wall that gets stronger, not weaker, the harder you try to push against it. And unlike its darker twin, a white hole never sits quietly, waiting patiently to devour something that wanders too close. It never rests. It never pauses. It continuously spews out streams of matter, blinding bursts of light, and staggering, almost unthinkable amounts of raw energy, seemingly from absolutely nowhere, as if reality itself were being fired out of a cosmic cannon that never, ever runs out of ammunition. If a black hole is the purest expression of hunger the universe has ever produced, absorbing everything it touches and returning nothing, then a white hole is the purest expression of eruption, releasing everything and absorbing nothing at all. It is, in the truest and most literal sense of the phrase, a cosmic repulsor, an object built entirely from outward force, with absolutely zero capacity to pull anything toward it, ever. There is another detail worth pausing on here, because it tends to surprise people the first time they hear it. A white hole is not simply a black hole with the arrows reversed on a whiteboard somewhere. It is what you get when you take the exact same equations describing a black hole and run the clock backward, mathematically, to the letter. Time reversal is a real, legitimate operation in physics, one you can apply to almost any equation describing motion. Apply it to the equations of a black hole, and a white hole is precisely, exactly, what falls out the other side. It is not a rough analogy. It is not a thought experiment invented for entertainment. It is the literal, formal, mathematical opposite of the object we just spent several minutes describing, sitting right there in Einstein's own field equations, waiting for anyone willing to look. Sit with that contradiction for just a second. One object that only takes. One object that only gives. Both fully permitted, both actually required, by the very same equations of general relativity that Einstein wrote down over a century ago. And that raises an obvious, almost unavoidable question. If these two things are mathematically perfect opposites of one another, mirror images down to the smallest detail, are they really two completely separate objects floating independently through the cosmos? Or is it possible, however strange it sounds, that they are secretly two ends of the exact same thing? Here is that question from earlier, the one I asked you to keep in your back pocket. Why has almost nobody heard of white holes, if they are just as mathematically real as black holes? Part of the answer is that we have never directly observed one. Every black hole photograph so far, including the famous image of the supermassive object at the center of the galaxy Messier 87, and the one released for our own galaxy center, Sagittarius A star, was detected because of how it swallows, by definition, would look almost the opposite, an object relentlessly pouring out matter and radiation from a region with no visible source feeding it. Some astronomers have even speculated that a handful of strange, unexplained high-energy bursts detected by telescopes could theoretically be candidates, though the overwhelming majority of physicists remain deeply skeptical, and for good reason, because there is a much simpler explanation waiting in the wings, one that does not require finding a single new object anywhere in the sky at all. This is exactly where the story stops being a simple comparison of who is more powerful, and turns into something far stranger than either object on its own. Back in 1935, Albert Einstein, working alongside physicist Nathan Rosen, proposed a solution to the equations of general relativity that mathematically connected the entrance of a black hole directly to the exit of a white hole, through a tunnel carved into the very geometry of spacetime. Today, this theoretical structure carries a name most people have at least heard once, an Einstein-Rosen bridge, though almost everyone simply calls it by its far more familiar nickname, a wormhole. Here is the question that makes this idea genuinely impossible to ignore. Every single second, all across the universe, black holes are pulling in staggering, almost unimaginable quantities of matter. Gas, dust, entire stars, in some cases entire smaller black holes get consumed and merged. The largest black holes we have ever detected, the supermassive giants sitting at the centers of galaxies, contain the crushed mass of billions of suns packed into their cores, material that has been accumulating, uninterrupted, for billions upon billions of years. So where does all of that material actually go? Matter cannot simply cease to exist. That would violate one of the single most fundamental rules underpinning all of modern physics, the conservation of mass and energy, a rule that has never once been broken in any experiment ever conducted. Something has to happen to all of that vanished material. It has to go somewhere. The wormhole hypothesis offers an answer that is, frankly, staggering to actually sit with. What if the singularity buried at the heart of every black hole does not represent an ending at all, but instead a piercing? What if the crushing, effectively infinite density hiding inside a black hole punches straight through the fabric of spacetime itself and comes out the other side, not necessarily in our own universe, but somewhere else entirely? Perhaps in another universe altogether. Perhaps folded into another dimension. Perhaps stretched out into another point in time, distant past or distant future. And what erupts violently on the other side of that impossible tunnel is exactly the object we just described a moment ago. A white hole, endlessly ejecting every scrap of that swallowed material back out into existence, somewhere else, forever. Under this model, a black hole and a white hole are not two separate monsters locked in some kind of cosmic rivalry, circling each other across the galaxy. They are the two mouths of a single, continuous structure, an entrance and an exit belonging to one unbroken tunnel, stretched across the underlying geometry of the universe itself. Everything that appears to vanish into darkness on one side might, somewhere, somehow, be exploding back into blinding light on the other. But this beautiful idea comes with a devastating problem, one that kept it firmly trapped in the realm of pure theoretical curiosity for decades after Einstein and Rosen first proposed it. Traditional wormhole models, built from the original, classical Einstein-Rosen geometry, appear to be catastrophically unstable. The moment even a single particle of ordinary matter attempts to actually pass through one, the tunnel collapses instantly, sealing itself shut faster than literally anything, even light itself, could possibly make it through to the other side. For a long time, this seemed to be the final word on the matter. A gorgeous, elegant mathematical structure, permanently trapped as nothing more than a beautiful impossibility, a poetic idea with no way to actually happen. And that might genuinely have been where this story ended, if not for one of the most radical ideas circulating in modern physics today, an idea that abandons cosmic tunnels altogether and instead completely rewrites our understanding of what is actually happening inside a black hole. Comes out of a field of physics called loop quantum gravity, and one of its leading, most vocal proponents is the Italian theoretical physicist Carlo Rovelli. The claim sitting at the very heart of this theory is almost absurdly simple to state out loud, and yet it quietly overturns nearly a full century of assumptions about what a black hole fundamentally is. According to this theory, a black hole is not a permanent grave. It is a caterpillar, and every single one, without a single exception, eventually becomes a butterfly. Pause here for a second, because this is worth repeating slowly. Not most black holes. Not the small ones, or the young ones, or some special rare category. Every single black hole that has ever formed anywhere in the universe, according to this theory, is already, quietly, on its way to becoming a white hole. The one at the center of our galaxy. The ones formed from the collapse of dying stars. The ones astronomers photographed for the very first time in 2019, and again in 2022. All of them, according to this framework, are mid-transformation right now, at this exact moment, while you are watching this video. Here is the actual reasoning behind that startling claim. General relativity predicts, cleanly and consistently, that matter falling into a black hole gets crushed down into a singularity, a mathematical point of truly infinite density and precisely zero volume. But quantum mechanics, the branch of physics that governs the smallest imaginable scales of reality, absolutely refuses to allow anything like that to actually happen. Quantum theory insists that space itself has a minimum possible size, a smallest conceivable unit of length, sometimes referred to as the Planck length, a distance so small it makes an atom look like an entire galaxy by comparison. Nothing anywhere in this universe, according to the strict rules of quantum physics, is ever allowed to be compressed down into a true mathematical point of exactly zero size. There is a flaw, a hard, non-negotiable limit built directly into the structure of reality. And all matter falling relentlessly into a black hole eventually slams straight into that flaw. So what actually happens when the crushing force of gravity meets an object that has already hit the absolute smallest size the universe will ever permit it to reach? According to loop quantum gravity, it cannot compress any further, not even slightly, and critically, it does not simply stop dead in its tracks. It bounces. Rovelli and his fellow researchers describe this moment as a state of maximum possible density, sometimes given the almost poetic name of a Planck star, describing the densest object the laws of quantum physics will physically permit to exist anywhere in the cosmos. And the very instant that limit is reached, the entire collapse violently reverses itself. The crushing, one-way implosion suddenly becomes an explosive, powerful rebound, with matter and energy recoiling outward with tremendous, staggering force. In other words, at that precise moment, the black hole quietly begins turning itself inside out. Now here comes the single detail that transforms this theory from merely strange into something that is genuinely, completely mind-bending, once you fully understand the relationship between gravity and the passage of time. Inside a black hole, gravity is so overwhelming, so extreme, that time itself slows down to an almost unimaginable crawl compared to how it flows for someone watching from safely outside. This is not idle speculation. It is a well-established, repeatedly confirmed prediction of general relativity, verified through real astronomical observation. According to Rovelli's model, the actual bounce itself, the precise moment where collapse abruptly turns into explosion, happens extremely quickly from the perspective of the matter that is actually undergoing it. But because of the extreme time dilation involved, that exact same bounce, when viewed from outside the black hole, from our perspective here on planet Earth, appears stretched out over an almost incomprehensible span of time. We are talking about a span measured in billions of years. This staggering fact means that a black hole which formed shortly after the very beginning of the universe could, right at this exact moment, still be somewhere in the middle of its bounce. The explosion, in a very real sense, has already technically happened. We are simply watching it unfold from the outside, in impossibly, agonizingly slow motion, stretched across a timescale that dwarfs the entire recorded history of human civilization finally completes, when a dying, slowly evaporating black hole has spent an unimaginable stretch of cosmic time quietly turning itself inside out. The theory predicts that it detonates. Not into nothingness, not into silence, but into a fully formed white hole, releasing absolutely everything it ever swallowed across the eons. Every crushed star, every consumed planet, every last fragment of information that ever crossed its horizon, all of it flung back out into the surrounding cosmos in one final, staggering, blinding burst of light and matter. If this model turns out to be correct, A white hole is not some abstract mathematical curiosity buried inside an equation, existing only on paper. It is the literal, inevitable destiny of every single black hole floating anywhere in the universe. Nothing gets erased. Nothing is ever truly lost forever. It simply waits, compressed down to the absolute limit the universe will allow, patiently, for its own precise moment to erupt spectacularly back into existence. It is worth being honest here, because a good story about the universe should never pretend to be more settled than it actually is. Loop quantum gravity is one serious, mathematically rigorous framework among several competing attempts to unify quantum mechanics with general relativity, and it has not been confirmed by direct experiment. No telescope has ever caught a black hole in the act of exploding into a white hole. No detector on Earth has recorded the signature Ravelli's model predicts. This remains, for now, one of the most compelling theoretical proposals in modern physics, not an established fact printed in a textbook. But that is precisely what makes it worth paying attention to. The history of physics is full of ideas that sounded like science fiction the decade before they were confirmed, black holes themselves included. Einstein's own equations predicted them in 1915, yet many physicists, including Einstein at times, doubted anything so extreme could actually exist in nature. It took over half a century, and eventually direct observational evidence, before the scientific community fully accepted that these objects were real, physical residents of our universe, rather than a strange mathematical curiosity. White holes, and the quantum bounce that may create them, could very well be sitting exactly where black holes once were, one confirming observation away from rewriting everything we thought we understood about how the universe recycles itself. Let that idea properly settle for just a moment, because it quietly reframes absolutely everything we started this video with. We began by describing two monsters locked in the most extreme possible opposition found anywhere in physics. One that consumes without any limit whatsoever. One that erupts without any limit whatsoever. One with a horizon you can enter but can never, under any circumstance, leave. One with a horizon you can never approach in the first place, no matter how you try. And yet, when you follow the mathematics, and now, potentially, the deeper quantum physics, all the way through to its logical conclusion, those two apparent opposites are not actually enemies locked in cosmic combat at all. They are two chapters belonging to the exact same underlying story. The universe, it seems, quietly refuses to allow pure, permanent destruction to exist anywhere without an equal and opposite act of creation patiently waiting somewhere on the other side of it. Every single point of absolute compression may ultimately be balanced, somewhere, at some point far off in time, by an equally absolute, equally violent release. Every apparent ending, encoded directly and permanently into the underlying mathematics of spacetime, quietly doubles as the seed of an entirely new beginning. So the next time you happen to see an image of a black hole, that now famous glowing, fiery ring of light bent dramatically around an abyss of total, impenetrable darkness, remember that you might not actually be looking at a graveyard at all. You might be looking at something closer to a chrysalis. Somewhere out there, perhaps unimaginably far away across the cosmos, perhaps unimaginably far off in the future, everything that has ever fallen helplessly into that darkness may currently be waiting patiently for its own moment to erupt spectacularly back into light. The single most destructive object we know of, anywhere in the entire universe, might, in the end, simply turn out to be nature's slowest, most patient, and most magnificent possible form of rebirth. What if I told you that throwing something away from Earth forever is actually easier than dropping it into the sun? Stop and think about that for a second. The sun sits 93 million miles away, a ball of fire so massive it commands everything in our solar system. And yet if you wanted to get rid of your worst nightmare, your most dangerous, most toxic, most radioactive piece of garbage, the sun is the one place in the universe you almost cannot reach. This is not a riddle. It is not a trick question. It is one of the strangest, most counterintuitive facts in all of physics, and by the end of this video you will understand exactly why humanity is permanently, physically trapped with its own mess, no matter how badly we want to launch it into that giant furnace 93 million miles away. Somewhere right now, in a storage facility, there are barrels of spent nuclear fuel that will stay dangerous for longer than human civilization has existed. And at some point, almost everyone who learns about that problem has the exact same thought. Why don't we just launch it into the sun? It seems so obvious. The sun is a bottomless furnace. It would vaporize anything instantly, permanently, with zero trace left behind. Case closed, right? Except it isn't, and the reason it isn't has nothing to do with politics, or cost overruns, or public opinion. It comes down to a piece of physics so counterintuitive that most people, including plenty of engineers who don't work in orbital mechanics, get it completely backwards on the first try. Here is the number that should stop you cold. The Sun holds 99.8% of all the mass in our entire solar system. Every planet, every moon, every asteroid, every comet, all of it combined is a rounding error next to that single, colossal star. Its gravity well is so deep that it keeps giant worlds like Jupiter and Neptune locked in orbit across billions of miles of empty space for billions of years, without them ever drifting free. Its core burns at 15 million degrees, hot enough to fuse hydrogen into helium, hot enough to erase anything that falls into it without a trace. So logic tells you the obvious thing. Just let go of an object in space, and that monstrous gravity will inevitably drag it down into the fire. Right. Wrong. And this is where astrophysics quietly breaks your brain. It is, in real terms, harder to crash something into the Sun than it is to fling that same object completely out of the solar system, past Pluto, past the Oort cloud, out into interstellar space forever. Read that again. Escaping the Sun's grip entirely is the easier task. Falling into it is the hard one. If that sounds backwards, that is because your intuition about gravity was built on watching things fall on Earth, not on understanding how bodies move through space. So let's take that intuition apart, piece by piece, because once you see the mechanism, you will never look at the Sun the same way again. The first thing you need to unlearn is the idea that Earth is standing still. It is not. Right now, as you listen to this, you are moving. Not walking, not driving, but hurtling through space on a planet that never stops. Earth orbits the Sun at 30 kilometers per second. That is 108,000 kilometers every single hour. To put that in perspective, a rifle bullet leaves the barrel at around 1 kilometer per second. Earth is moving 30 times faster than a bullet, permanently, and everything standing on its surface, including you, including every rocket ever built, including every ounce of nuclear waste sitting in a storage facility, is moving at that exact same sidewise velocity right along with it. This is the part almost nobody accounts for when they imagine just launching trash at the Sun. A rocket does not start from zero. It starts already carrying Earth's full orbital speed as sideways momentum, baked in from the moment it leaves the launch pad. Point that rocket dead center at the Sun, fire the engines, and here is what actually happens. The object does not fall into the Sun. It just falls into a new, stretched out orbit around it. Because it is still carrying all that sideways speed, it swings past the Sun and loops right back out again, forever, an eternal ellipse that never touches the surface. You can aim as precisely as you want. Perfect aim is not the problem. The problem is velocity you are carrying that has nothing to do straight down while you are sprinting on a moving train. No matter how hard you throw, no matter how perfectly you release it, the ball inherits your forward speed. It does not fall straight down beneath you. It arcs forward and lands way ahead of where you are standing. Space works exactly the same way, just on a scale of 108,000 kilometers per hour instead of a light jog. If you actually want an object to fall straight down into the Sun, you cannot simply point it there. You have to cancel out that sideways speed completely, all 30 kilometers per second of it. You need to hit the brakes so hard that the object goes from racing sideways at rocket speed to sitting dead still relative to the Sun. Only then does gravity finally take over and pull it straight down into the fire. And that single requirement, killing 30 kilometers per second of sideways velocity, is where the entire plan collapses under its own weight. Because braking in space is not free. It costs fuel. A staggering, almost absurd amount of fuel. Let's actually run the numbers, because this is where the idea goes from difficult to basically impossible. If you wanted to send a rocket completely out of the solar system, escaping the Sun's gravity forever and drifting off into interstellar space, past every planet, past every trace of home, you would need to add roughly 12 kilometers per second of extra speed on top of what Earth already gives you for free. 12 kilometers per second. That is the escape ticket to leave the entire solar system behind. It sounds enormous, and it is, but compare it to the other option. To cancel out Earth's orbital velocity and actually fall into the Sun, you need to remove 30 kilometers per second. Not add. Remove. And removing velocity in a vacuum takes just as much propellant as adding it, because there is no air, no friction, nothing to slow you down for free. Every kilometer per second you want to shed has to be paid for in rocket fuel, just like every kilometer per second you want to gain. So compare the two numbers honestly. 12 kilometers per second to leave the solar system forever. 30 kilometers per second to fall into the sun. Falling into the sun costs 2.5 times more energy than escaping the entire solar system. Read that sentence one more time, slowly, because it is the single most counterintuitive fact in this whole story. It is objectively, mathematically easier to throw something at Alpha Centauri than it is to throw it into our own star. Let's slow down for a second, because this is usually the point where people assume there must be some clever trick. Maybe you use a bigger engine. Maybe you use a more efficient fuel. Maybe you launch from a different angle. None of that changes the underlying math, because the problem is not engineering cleverness, it is raw physics. Velocity is velocity, whichever direction you need to cancel it in, and space does not offer any discount for effort or ingenuity. There is no clever trajectory that lets you skip the requirement to remove 30 kilometers per second of sideways motion. You either pay that cost in fuel, or you never actually reach the sun. Every other detail of the mission is negotiable. This one number is not. And this is where the rocket equation turns from an inconvenience into an outright trap. In spaceflight, there is a brutal, unforgiving law named after the scientist Konstantin Tsiolkovsky, and it says something simple but devastating. Every extra kilogram of fuel you carry to slow down also has to be lifted off the launch pad in the first place, which means you need even more fuel just to carry that fuel, which means you need more fuel to lift that fuel, in a spiraling chain reaction that gets worse and worse the more braking power you demand. It is not a straight-line cost. It is exponential. Want to remove a little velocity? Fine, a reasonable rocket can do that. Want to remove 30 kilometers per second of velocity for a heavy payload, and the fuel requirement does not double or triple, it explodes into something actually looks like in real hardware. The Saturn V, the rocket that carried astronauts to the moon, is still one of the most powerful machines humans have ever built. It stood over 100 meters tall and burned through roughly 2 million liters of propellant just to escape Earth's gravity and coast to the moon, a trip that required nowhere near the braking demands of a solar dive. Now imagine trying to send just 1 single ton, 1 metric ton, of waste on a direct path into the sun. To cancel that 30 kilometers per second of sideways speed for that cargo, you would need a rocket that dwarfs the Saturn V, a machine so large and so fuel heavy that building and launching even one of them would strain the resources of an entire space program. And remember, that is for 1 ton. Nuclear waste alone, worldwide, is measured in hundreds of thousands of tons. You are not talking about building one giant rocket. You would need an entire fleet of rockets, each one bigger than anything humanity has ever launched, flying constantly, for decades, just to move a fraction of the problem off the planet. The math does not just make this expensive. It makes it fundamentally, structurally impossible with any technology we currently possess or are likely to possess for a very long time. There is one more way to picture the scale of this problem, and it might be the clearest one yet. Every kilogram of braking fuel you add to a rocket is dead weight sitting on top of the vehicle before launch, weight that has to be lifted off the pad along with everything else. To lift that weight, you need more engine thrust and more fuel underneath it. But that new fuel has weight too, so you need even more fuel to lift it, and the cycle repeats, layer after layer, like a pyramid scheme that never pays out. Engineers sometimes call this the tyranny of the rocket equation, and it's not an exaggeration. It's the single biggest reason spaceflight is difficult in the first place, and it's also exactly why braking hard enough to fall into the sun turns from a bold idea into a mathematical dead end. Now, at this point, a sharp listener is going to push back. Wait a second. Haven't we already sent spacecraft close to the sun? What about the Parker Solar Probe? What about missions to Mercury? If human engineers already solved this, why am I being told it is impossible? This is the exact right question, and the answer reveals just how narrow the actual solution is. Yes, there is a way to cheat the fuel trap, and it is genuinely one of the most elegant tricks in all of orbital mechanics. It's called a gravity assist, sometimes nicknamed a gravitational slingshot, though in this case it works in reverse, as a brake instead of an accelerator. Instead of burning fuel to cancel your velocity, you fly close past a planet, let that planet's gravity bend your path, and hand off a slice of your unwanted speed to the planet itself in the process. Do that enough times, with enough planets, in exactly the right sequence, and you can gradually bleed away your sideways velocity for free, using nothing but careful navigation and the gravity of worlds you're passing by. This is exactly how NASA's Parker Solar Probe managed to dive closer to the Sun than any spacecraft in history, repeatedly swinging past Venus to shed velocity bit by bit until it could drop into an extremely close solar orbit. It is exactly how the European and Japanese Bepi Colombo mission is making its long journey to Mercury right now. But look closely at the price of this trick, because the price is time, an enormous amount of time, and precision so exact that a single miscalculation ruins the entire mission. Bepi Colombo does not go straight to Mercury. It has to perform 9 separate flybys, 1 of Earth, 2 of Venus, and 6 of Mercury itself, each one bleeding off just enough velocity to bend the trajectory a little closer, over a journey that takes more than 7 years just to arrive and settle into orbit. 7 years, 9 precision flybys, for one single spacecraft that across an industrial-scale garbage disposal operation. Imagine trying to send not one probe, but thousands of tons of nuclear waste, or chemical byproducts, or any other hazardous material humanity wants to be rid of, using this same 7-year, 9 flyby dance. Every single shipment would need its own perfectly threaded trajectory through multiple planetary flybys, timed to planetary positions that only align in specific windows, tracked and adjusted for years at a time, with zero room for error, because a miscalculated flyby doesn't just delay the mission, it can fling an out-of-control payload in an unpredictable direction entirely. You are not describing a disposal system anymore. You are describing an ongoing celestial ballet involving every planet in the inner solar system, repeated endlessly, forever, for garbage. No space agency, no government, no combination of governments on Earth has anywhere near the tracking infrastructure, the launch cadence, or the sheer navigational bandwidth to run that operation at any meaningful scale. The gravity assist trick works beautifully for one scientific instrument. It collapses instantly under the weight of industrial waste disposal. And even if, somehow, humanity solved the fuel problem and solved the traffic control nightmare of thousands of gravity-assisted trajectories running simultaneously, there is one more obstacle standing in the way, and this one has nothing to do with orbital mechanics at all. This one is about what happens the moment something goes wrong on the launch pad, or seconds after liftoff, while the rocket is still climbing through Earth's own atmosphere. Because here is the uncomfortable truth about rocketry that nobody likes to say out loud. Even today, with all our advanced engineering, all our computer modeling, all our decades of accumulated experience, rockets still fail. Modern launch vehicles, some of the most reliable machines ever built, still carry a failure rate hovering around 2 to 3%. That might sound small. In almost every other context, a 97% success rate would be extraordinary. But run the math on what that 2 to 3% actually means when the payload changes. When an ordinary communications satellite explodes on the launch pad or fails during ascent, it is a tragedy for the company that built it and an expensive lesson for the engineers. It is a financial loss, sometimes running into hundreds of millions of dollars, and nothing more. The satellite falls into the ocean or burns up, and life goes on. But now replace that satellite with thousands of tons of spent nuclear fuel rods, or with barrels of concentrated chemical toxins, exactly the kind of material that would motivate someone to try shooting it into the sun in the first place. Run that same 2 to 3% failure rate across the hundreds or thousands of launches an industrial-scale program would require, and simple statistics tell you that a catastrophic failure is not a remote possibility. It is a mathematical inevitability. Somewhere along that production line of launches, one of them will fail, and when it does, it will not fail quietly in the vacuum of space. It will fail while it is still climbing through Earth's own upper atmosphere, exactly the layer of air where high-altitude jet stream winds are strong enough to carry fine particles across entire continents in a matter of days. In other words, a rocket carrying radioactive or toxic cargo that explodes during ascent does not disappear. It becomes, instantly and by definition, one of the most effective dirty bombs ever created, except detonated by accident, at high altitude, with no target and no way to contain the fallout. The very winds that circulate our planet's weather would become the delivery mechanism, scattering lethal material across oceans and borders in exactly the way we spent decades trying to prevent through nuclear treaties and containment protocols. The plan to protect Earth's future by launching its most dangerous waste that the Sun carries, built directly into its own execution, a real and recurring chance of causing exactly the global contamination event the entire plan was supposed to prevent. You do not eliminate the risk of nuclear waste by trying to launch it away. You just change the shape of the risk, and arguably make it worse, faster, and hiding underneath all of this that rarely gets mentioned, one that has nothing to do with rockets at all. Even setting aside the fuel, the flybys, and the failure statistics, who exactly would agree to let this happen over their heads? Rocket launches already require flight corridors over open ocean, precisely so that if something goes wrong, debris falls somewhere empty rather than somewhere populated. Multiply the number of launches into the hundreds or thousands needed for a real waste disposal program, and you are asking the entire world to accept a permanent, recurring chance of catastrophic fallout, indefinitely, in exchange for a plan that international treaties on nuclear material and orbital debris would almost certainly forbid before a single rocket left the ground. This isn't just a technical problem. It's a problem no government could get approved even if the engineering somehow worked. So let's step back and look at the full picture, because every piece we've walked through locks into the next one like a chain, and none of them offer an exit. Earth carries you through space at 30 kilometers per second whether you like it or not, and that speed has to be cancelled, not ignored, before anything can actually fall into the sun. Cancelling that speed costs more energy, more fuel, and more raw engineering than escaping the solar system entirely, which makes a direct shot at the sun the single most expensive maneuver in all of practical spaceflight, harder than reaching any other destination in the galaxy we could realistically aim. 4. The one workaround, slow gravitational slingshots past multiple planets, does exist and does work, but only at the tiny, patient scale of a single scientific probe taking the better part of a decade to arrive, a method that cannot possibly be scaled up to industrial waste removal without collapsing under its own logistical weight. And even if you found a way past all of that, the simple statistical reality of rocket failure rates means that any large-scale launch program carrying hazardous material will, sooner or later, fail during ascent and turn our own atmosphere into the delivery system for exactly the disaster we were trying to avoid. Every single layer of this problem reinforces the others. Physics blocks it. Fuel economics blocks it. Navigational complexity blocks it. And basic safety statistics blocks it one final time, just in case anything managed to slip through the first 3 walls. So here is where that leaves us, and it is worth sitting with for a moment. The Sun, despite holding almost all the mass and all the gravity in our entire solar system, is functionally unreachable for the one purpose we might actually want it for. We cannot use it as a cosmic incinerator. We cannot quietly launch our nuclear waste, our worst chemical byproducts, our most permanent environmental headaches, off the edge of the world and let a star billions of years old simply make them disappear. The math will not allow it. The fuel will not allow it. The safety statistics will not allow it. Every law of orbital mechanics that keeps our planets locked in stable, beautiful, predictable orbits for billions of years is the exact same law that traps us here with everything we have ever created, good and bad alike. We live on a platform that never stops moving, sealed inside a gravitational system with only one real exit, and that exit points outward, away from everything, not down into the fire. There is no cosmic trapdoor. There is no orbital shortcut waiting to be discovered by a clever engineer with a big enough rocket. The sun will keep burning at 15 million degrees at its core for billions more years, magnificent and untouchable, and every single problem we create down here on Earth is going to stay right here with us. Not because we lack ambition, and not because we lack technology, but because the universe itself, through pure unforgiving physics, has quietly decided that this one most important takeaway buried inside all this orbital mechanics. We tend to imagine that with enough rockets and enough money, humanity can eventually throw any problem far enough away to stop worrying about it. Space feels infinite, and infinity feels like it should have room for our mistakes. But the sun sitting right at the center of our own solar system, the one object massive enough to seemingly solve everything, turns out to be the single hardest target in the entire sky to actually hit. The same orbital momentum that keeps our planet gliding safely around that star for billions of years, never spiraling in, never drifting away, is the exact same momentum that makes it almost impossible for us to send anything the other direction. It is a strange kind of cosmic irony. The very stability that allows life to exist here in the first place is what permanently seals off our easiest imagined escape route for what we create. So if we want a future without mountains of nuclear waste and toxic byproducts, we are not going to find it 93 million miles away. We are only ever going to find it by solving the problem right here, on the same fast-moving, gravity-bound planet where we made it in the first place. The sun was never going to save us from ourselves. It was never even a possibility. And once you understand the physics behind why, you start to see this planet a little differently, not as a launch pad with an escape hatch, but as the only place we actually have, moving through space together, mistakes and all.